All right, we'll start recording. Admit all. All right. Nice to see you all there at home. Okay, so for today, there's my cursor. We are looking at, we started water chemistry last class. So we'll spend some more time on water chemistry stuff. And even though it says water continued and then water on the next one, I think we'll finish up water chemistry today and probably get into like carbon and biomolecules and stuff like that. And the reason that that's interesting is this is where we learn, and I taught my 9th graders a little bit of it, but like methamphetamine and how that works and some various things like that that are kind of odd. So some of the stuff in that first day packet, we're going to start like learning some of those things today. And today is also when it starts to feel, we're kind of transitioning out of feeling like a chemistry class and transitioning into feeling much more like a biology class. So chemistry still explains a lot of stuff, but it'll feel like we're talking about bio by the time we're at the end of class. Does anybody have that first day packet thing that they want to turn in? If you do, just kind of hold it up and I'll come around and grab them. Thank you. Thank you. Thanks. Thanks, thanks. Thank you. Thank you, thank you. Some people turned it in already, so if you're like, I thought I already turned it in, you might have. Thanks. Got it? Thank you. Thank you, thank you, thank you. If you're at home on the Zoom meeting, you probably did the digital version instead. You probably did that Google survey, so you don't have to give me a paper copy. All right. How you doing, Sydney? Cool. 1 thumbs up. All right. Everybody else out there okay? Out there on the home front? One yes. Yep. All right. Silence is golden. Okay. So let me go ahead and get rid of this. And we'll pick up with some water stuff. Oh, there's a cute little baby. That's from an experiment in my 9th grade class. We did not experiment on the baby, just to be clear there. Okay, let me drag over this picture. And I think we'll be ready to actually legit start class. Morning. And then one last thing to change. We'll switch angles for a second. All right, so last class, we were focused a whole lot on water chemistry stuff. So we kind of had like 1, 2, 3, we had a few things numbered. I kind of teach my classes until we run out of time. So some teachers, have you ever been in a class where a teacher will be like, maybe you're in 4th period or something, and the teacher's cruising along and they're like, well, that's where I stopped in 2nd period, so that's where we'll stop. Now you guys kind of have free time. I don't really do that. And so on one hand, it's good because we teach and learn the whole time. On the other hand, it's bad because when I stand up here, like, I never really know exactly where we left off. We got a pretty good idea. So normally I start off class by saying like, did we leave off right about here? So I was numbering stuff. Did we leave off at about like number 3 or something like hydrogen bonds or cohesion? Which one was it? Do you know? Was it hydrogen bonds? About to get to hydrogen bonds? Okay, so when we were looking at water chemistry, the first thing that was important, I guess water was bent. I don't think I numbered that one, but water has like a bent shape. And then what was the first important thing about water chemistry that kind of like begat all the other things? Sorry, I got a little bit biblical with the words there. I was trying to be interesting. Yes? Yeah, oxygen has a really high electronegativity. I'll just say electronegativity. And hydrogen is more like kind of medium to lowish, whatever you want to, however you want to say it. Or to be more specific, oxygen's was like 3.5, and hydrogen's was like 2.1. All right, so fine. What did that cause? Or remind me, somebody else tell me what was electronegativity. electronegativity. And I'll actually, let me throw that to the home crew real quick. Does anybody want to tell me what electronegativity is? You can just unmute. Anybody at all? I want to connect with my home crew. Silence. All right. How about? Oh. Yeah, that's good. Valerie says very confidently. So with high electronegativity, you hog electrons harder than if you have low electronegativity. And so why does that matter? Like, what does that cause? That causes number 2. What was number 2 again? Is it easier if I kind of like direct a question at like, hey, live class is a question for you, or remote it's a question for you? Is that better for you guys, or is it better for me to just throw it out there for everybody? All right, okay. I'll throw it out, and then every once in a while, if I feel like I'm not getting as much involvement from the home crew, I'll kind of throw one directly at you guys. Okay, back in the back, what do you think? Yeah, water is polar, good. So water is polar. And somebody from the home crew, remind me, what does polar mean in chemistry? Say that one more time, just a little bit louder.
Does it mean opposite?
Yeah, it means opposite. Good. So it's opposite. And then somebody that's live, what's opposite about it? Like opposite colors or? Yeah, charges. So water's polar, meaning it has a slight negative and slight positive charges. And who was it that had the negatives? This is for anybody. Yeah, oxygen. So I've got water, and over here, my oxygens have slight negative charges on them. My hydrogens have slight positives. I'll write that a little bit darker for the home crew. $71. Is it not warm in here? It does feel warm? Okay. I saw 71 and I'm warm and I'm like, well, there you go. Guess I'm getting ready to get quarantined. Let's see. Quick little note. Let's see. I think I've taught 3 of y'all previously. How many of y'all that I taught previously, my air conditioner in this room broke during your year? All 3 of them. So yeah, my air conditioner typically breaks twice a year. And usually one of them is right about now. So fingers crossed, hopefully it's okay. So here's water. There's a slight negative charge around the oxygen. There's slight positive charges around the hydrogen. And so because of that, number 3. What's number 3? And we might have written down number 3, or we might be ready. Okay, we're ready for number 3. So number 3 is this. If I've got a water molecule, like let me put one over here, and I put another water molecule right next door, like this, are the water molecules going to stay like that? Why not? Why will they not stay like that? Say that again? Yeah, opposites attract. What's the charge on that hydrogen? Slight positive. What about that one? Slight positive. So what would these water molecules do? They'd repel. So they'll repel apart. You think that whenever you like take some water and swirl it around, that the water molecules are just in there random, but they're not. If you basically like move these around and put them side by side, then what they'll do is they will actually on their own, oh, there it is, sorry. Add that student in. Then they will on their own like rearrange. And because opposites attract, it will look something like this. And then home crew, remind me, is it better with the lights like this, as they are now? Or is it better like that? So this is second option. Is it better the way that they were, or is it better the second option?
It's better right now.
Okay, cool. Right now. Wait. Sorry, I messed that up. Like it is currently. Okay, cool. Okay, so I've got these water molecules, and they're attracted to each other. Well, that attraction has a name. Yeah, hydrogen bonds. Hydrogen bonds are always represented with dotted or dashed lines, like that. Okay, so one of the things that I told you about water chemistry is the way that we learn water chemistry should be the way that you learn biology all year long. So I'll show you what that means in a second. A lot of y'all are writing, so I'll wait for you. I don't see any questions in the chat. Everybody on the home crew doing okay then? Excellent. Thanks, Sydney. Everybody else is still actually there, right? You're not like in the other room eating Cheetos?
Yeah, we're here.
Uh-huh. I can hear the Cheetos. Just kidding. Okay, so two responses out of 11. I think this is going great. Okay, so we got hydrogen bonds. I got to find a way to make sure I have my home crew involved. When I just look out there and I see a letter A or like Curious George, it makes me sad. So we've got hydrogen bonds, and hydrogen bonds happen between water molecules. And why do hydrogen bonds happen? Because water is polar. Why? What does that mean? Water has slight negative and slight positive charges. Why is water polar? Because oxygen hogs electrons more than hydrogen does. So this thing causes this thing, which causes the next thing. So number 4, cohesion. Cohesion is when a substance like X sticks to another substance of X. So that's like water sticking to water. So X sticks to X, water sticking to water. That's what's happening right here. And again, the way that we kind of understand water is how we want to think of all of biology. So I'll pause for a second. You guys are writing. Hey, a few more of y'all are showing your faces. That makes me so happy. And again, it's okay if you don't. You might have reasons not to. Okay, so now, think of it this way. Cohesion is when water sticks to water. Well, what was the cause of that? Well, water forms hydrogen bonds, which are always represented by dotted lines. Why? Because each water molecule has slight negative and slight positive charges called polarity. Why? Because oxygen hogs electrons harder than hydrogen does. This leads to this, leads to this, leads to this, leads to the next one. Number 5, the other adhesion, adhesion. This is when water, X, sticks to non-water, like Y. So adhesion is when X sticks to Y. And we'll try a few examples. I think a lot of y'all did these in 9th grade. Okay, so water can stick to something that's not water. Why? Because of hydrogen bonds. Why? Because water's polar. Why? Because oxygen hogs electrons. Okay, so now let's do a couple of like kind of thought experiments. Let's say that I've got a table like this, and I pour some water in the middle of the table. And so the water eventually makes it over to the side. Kind of like if I poured water on this table, it eventually makes it to the side. So when it gets to the side, as soon as it touches the side, does it fall off? Or does it kind of like seem to sort of pile up? Like it looks like a peninsula going out there at first, but then does it usually like fall off right away, or does it sometimes sort of pile up and then like it might pile up and it sits there until you touch it and then it all falls off? Doesn't it usually pile up and then fall, or pile up and you have to touch it and it falls? So why is that? Why doesn't the water just as soon as it gets to the edge fall off? Yeah, basically it's adhering to the table and then it's cohesive with all the other water molecules. So picture it this way. Let's say that we're all running towards a cliff. I don't know why. And none of us are holding hands or anything. And we're running towards the cliff and we get to the edge, we just fall off. But instead, let's say that we're running towards the cliff, but we're all like arm in arm. And the front row's like, oh no. And then the second row, the third row, and the fourth row like locks up the brakes. If we're all like linked arms, won't I kind of like hang off the edge of the cliff? Then you guys might pull me back. That's what's happening. If this desk was clear, and I said, how many students can we get to stand on this desk? And you just have to stand like this. How many can we fit up here? Maybe it's 10. But if you guys could like lock arms and hold on to each other, couldn't we fit like 12 or 13 students probably? Somebody be like halfway hanging off the edge, something like that. So cohesion, water sticks to water, and then water can also stick to the countertop, adhesion. Let me give you another example. Paper towel. This is the best example. This is a paper towel. And I don't have any wax paper, but wax paper and laminated paper are kind of similar. So if I've got a puddle of water and I stick the corner of this paper towel into the puddle of water, what does the water do? Does it stay down here? No, it kind of goes up, right? So it's adhering to the paper towel, right? How high does it go? Like if I just barely touch that corner, doesn't it go like at least an inch or so? Isn't that probably billions or trillions of water molecules tall? I mean, normally when you're talking about molecules of water, you use like a mole, don't you? 6.02 times 10 to the 23rd. So it's got to be billions or trillions. So it's fighting gravity, billions or trillions of molecules high. Okay, so I'm going to throw this one out to the home crew first. You guys ready? They're all terribly excited. I know that you guys can't see it, but they are. Ah, thank you, thank you. Thank you, Curious George. So I put this in here, and it starts to go up. So my question is this. What do I know about this piece of paper? Like from a chemical properties standpoint, what has to be true about this piece of paper? It's not an easy question. So home crew first, and then we'll go with the live crew. It is absorbent, that's true. So somebody here live, can you help her out? That's true, it's absorbent, but let me say it this way. My wax paper, if I dip my wax paper in there, does the water go up it? So it's non-absorbent. Why? Like obviously, well, that one has wax on it, but why is this one absorbent and this one's not? What chemical properties do I know about this that's different from the chemical properties of my wax paper? That's true. This is kind of quilted, so the water molecules can kind of occupy those air pockets. So that's true. That will make it better at absorbing. But even if, and I don't have any, even if we had those crappy like kind of tan paper towels that are in like the bathrooms and stuff around here that aren't quilted, it'll still soak it up, right? Now this will soak it up better, I agree. Why is it that the wax paper, in fact, if I put a drop of water on the wax paper, it won't even stick, it'll just slide off. I can roll it around like a little soccer ball. If you got nothing going on, if you're at home and you're bored of being at home, get you some wax paper, water, play a little bit of soccer. It's therapeutic. Yes? Yes, the wax paper is nonpolar, and what about this paper? It is polar. So this paper actually has charges all over it, pluses and minuses everywhere. So if I could look at the chemical structure of this, my regular piece of paper is by the way, you guys at home, whenever I write something up there, is it like right side or is it like flip-flopped?
It's right side.
Okay, cool. If it's ever flip-flopped, let me know. I can flip it back. Because currently I have to have one of my settings set on flip-flop for it to look right for you guys. So just always let me know if it's ever flipped. I know how to fix it. Okay, so here's my paper. Here's kind of like the chemical structure of my paper with pluses and minuses. So imagine in this classroom, we're all water molecules. So here we are, trying to make this as realistic as possible. Okay, it's funny in my head sometimes. So now, we're all water molecules, and this wall right here is this white sheet of paper. Not wax paper, just regular paper or paper towel. And it's going to be dipped into us. So that paper now has all these pluses and minuses. Now these are a little bit small, so if you're in the back or you're watching from home, I'm just drawing tons of pluses and minuses on the board. I'm a water molecule. You guys are water molecules. So what happens if I get near one of you guys? Do we attract or repel? We attract. We stick with hydrogen bonds. That's called cohesion because we're each polar, because oxygen hogs electrons. So we're going to all start sticking to each other as soon as we touch. Now, I'm over here and I touch the paper. Am I attracted to that paper? Yes. My oxygen head is negative. My hydrogen hands are not. So I'm a water molecule. This is negative. These are positive. So what I'll do is as soon as the paper is dipped into me, I like slam my head against that positive right there. So I'm just like, pow. And when I do that, my positive hand is attracted to that negative. So I'm like, pow. But when I do that, that peels my head off. And so then this hand is attracted to that positive, pow. And before you know it, I do this. I'm like, all the way up the piece of paper. And why do you guys follow me? Because of cohesion. So we're all attracted to each other. If one of us is attracted to the paper, we just keep on climbing up, and then you guys are attracted to the paper. And so we basically go until the force of gravity outweighs the force of adhesion. So that's how absorption in paper towel works. If instead I have wax paper is nonpolar. So am I attracted to this paper at all? No, so dip wax paper in water, take it out, the water doesn't stick. No hydrogen bonds. If I'm making brownies, you guys at home, you have an advantage. You could be making brownies right now. Why aren't you? So you make some brownies, you're letting them cool. Well, at my house, our family has a golden retriever. Golden retrievers are really hairy. So you got yellow lab, that's the short hair. Golden retrievers are the ones that have like tons of hair. So let's say our golden retriever's running around in the kitchen, and I've got like brownies, just the pan open to the air, drying out. Couldn't I get like a dog hair in there or something disgusting like that? So I cover them, right? So I could take a piece of paper towel and cover the brownies. I'll mash that down on there. Or I could take some wax paper and cover the brownies and mash it down on there. Come back 30 minutes later. When I try to peel the regular paper off of the brownies, doesn't it stick? Yes. Why? Because it's hydrogen bonding with my brownies. What about the wax paper? Does it stick? In general, no. Why? Because it's not hydrogen bonding with my brownies. So, next time you're on a date, you're kind of running out of stuff to talk about, wax paper and brownies. It's a good one. That's why I always bring a pen on a date. Because then, when they're like, what are you talking about? I was like, hand me that napkin, I'll show you. So see, oxygen hogs electrons more than hydrogen. And this polarity. So give it a shot. See how it goes. I bet it'll work wonders. Okay, so after adhesion, let me go back. I'm going to try to kind of stay in order here. Hydrophobic, surface tension, high specific heat. Okay, another one that's kind of related to cohesion is this one. We'll get to see some cool biology stuff in just a second. Like I said, we're getting ready to transform into a bio class instead of a chem class. But one of the properties that relates to cohesion is, you can say, like high heat capacity. High heat capacity. If you wanted to be fancy, high heat capacity is like high specific heat and high heat of vaporization from chemistry. So we just say high heat capacity. So in chemistry class, you might have learned that specific heat was like how much energy it takes to raise 1 gram or 1 milliliter of water 1 degree Celsius. And heat of vaporization is how much energy does it take to make this water turn into a vapor. All that together is high heat capacity. Turns out in nature, water has one of the highest heat capacities of anything found in nature. And you're like, don't care, Mr. Cotton. All I'm thinking about now is brownies. Well, why does that matter? What does it mean if you have a high heat capacity? Like, pretend that this substance, this marker, had a high heat capacity, and whatever this substance represents, and this substance does not. What's different about them? Yeah, it takes more energy to heat them up, whether they're going to heat up and turn into a liquid or just get warmer. So, aluminum. Does aluminum have a pretty high or pretty low heat capacity? What do you think? If I took an aluminum pan and turned on the flame, let's say you have a gas stove, and I turn it on, and I touch it 30 seconds later, is it already getting pretty warm? Yeah, so it has a low heat capacity. What if I take water and I put it on the stove, and I've got the flame on high for 30 seconds, and I stick my finger in there? Can I even sense a difference in temperature much? Probably not. It might have gone up a degree. I don't know. How many 100-degree days have we had? But if you had a swimming pool and you watched, it's 100 out, and your pool is like 80. 5 hours later, it's like 81. 5 hours later, it's like 82. The swings on a swimming pool are about 2 or 3 degrees throughout the day. And the temperature is changing between, 105 and feels like 105 and 103, but it's like 105 and down to like 80. So water has a high heat capacity. That means it takes forever for it to heat up. Why does water have a high heat capacity? Because water sticks to water, cohesion. Why? Because hydrogen bonds form between water molecules. Why? Because water is polar. Why? Because oxygen hogs electrons. Why do I care that water has a high heat capacity? Like, do it? Yeah, depending on how hydrated you are, you're about 70% water, 65% water. So what would happen to us if water had a low heat capacity? What would be different in life? Living in Texas. Say that again?
Body temperature?
Yep, my body temperature. So let's say that my body temperature right now is 98, 99. And I go outside. I'm sure it's hot out there, even though it's overcast. I'm sure it's hot. What's different if water has a low heat capacity? What'll happen to my body temperature? Yeah, it goes up faster. So if water had a really low heat capacity, like on the way to my car, it'd be like 99, 100, 101, 102, 103, 104. When do you die, by the way? Yeah, around 108 is when brain damage usually kicks in. And the older you are, the worse it is, like everything. But around 110 is when people start dying. It's kind of weird. You're like 10 degrees away from death. If you're at 98, you're 10 degrees away from brain damage. Sort of bizarre. If I go outside, I bet I can't estimate the temperature to within 2 degrees. Now, I kind of know what the temperature is always going to be right now, so whether I go outside or not, I'm going to guess. It rains, so I'm going to guess like 84. But like if I went outside and it was 84 versus 86, I bet I couldn't actually sense the difference. I can't sense 2 or 3 degrees, I bet. But like if I'm at 98 or 99, I'm always 8 or 10 degrees away from brain damage. Just sort of weird. If I'm down to 90, I freeze to death. We're super fragile. But because water has a high heat capacity, I can go outside and it's 100 and I slowly heat up. Okay? Now, once it's hot, what's my body going to do to cool me off? Sweat. What's sweat mostly made out of? Water. So water, a little bit of sodium, a little bit of potassium, electrolytes. Have any of y'all ever seen Idiocracy? Nobody. Okay, another story for another time. It's an electrolytes joke, but nobody's going to get it. In Idiocracy, the premise of the movie is supposed to be funny. It's actually not very funny, but there's this government, everybody intelligent dies, and there's only dumb people. There's one average Joe that survived, and now they think he's brilliant because everybody else is an idiot. And so Gatorade had always told them that you need electrolytes, so they thought electrolytes are good. And so they water all their crops with Gatorade, and they can't figure out why they're dying. And so the guy's like, well, you don't use Gatorade, that'll kill them. And they're like, but it's got electrolytes, and electrolytes are good for you. And so he's trying to explain this to them. So anyway, your sweat is mostly water and a little bit of electrolytes. Anything that carries electricity is an electrolyte. So when I go outside, water has a high heat capacity. So if I cover my arm with a thin layer of sweat, so it's liquid, and then as I sweat, doesn't it eventually evaporate? It does. So I got outside, it was liquid. Now it's a gas. What do I have to add to water to make it turn into a gas? If I'm in the kitchen and I have liquid water and I want it to be a gas, what do I have to do? Yeah, I add heat. So let's say it's really hot in here. The lights are off, so there's no sunlight. But there's a fan. I cover myself with water, sweat. It evaporates. So that means I had to add heat to the water, right? Where did the heat come from? Could be the environment. Came from me. So I cover myself with water. My body heats up the water. It evaporates. So now, heat just left my body. How does it feel when heat leaves my body? Cool. So sweat cools me off. Have you ever been to, like, say, maybe you're in Colorado and it's 90 and you sweat and it really, really cools you off? You step into the shade and it's freezing. Whereas here or down in Houston, you step into the shade and it doesn't feel a whole lot cooler. That's because here it's super humid, so you're just drenching in sweat. You're hiking in Colorado, working your butt off. It's like 90 out. You don't feel any sweat because as soon as it hits your skin, it evaporates. So you cool off a lot in Colorado. Here, you sweat, it doesn't evaporate, so you don't cool off. So that's the heat index. That's why when it's super humid and you sweat, it doesn't help. You're just dripping sweat, but it doesn't actually feel cool. If you wear a special shirt, one of those dry wick whatever shirts, Nike, Reebok, whatever, they're supposed to dissipate that water and have it evaporate faster, so it'll cool you off faster. That's how it's all supposed to work. So water has a high heat capacity, which means I can cover myself with a teeny tiny amount of water, and when it evaporates, it takes away a whole lot of heat. If water didn't have a high heat capacity, I would have to sweat twice as much, 3 times as much, 4 times as much, 5 times as much, and then I'd dehydrate and die. So when I walk outside and it's hot, first of all, my body temperature very slowly increases because water has a high heat capacity. Then when I sweat and it leaves, it takes a ton of energy with it, so that hopefully I can sweat and slowly raise my body temperature. So that's why it matters. All right, let's look at one other thing that we need for kind of AP Bio, and then I'm going to show you one that's just kind of fun. It's a fun water fact. I mean, there are many, but I'm just going to pick one. Let's say, hey, no problem.
Starting Friday, I'm going to do this
Okay,
I just wanted to come
cool,
and see.
awesome. Yeah,
Okay,
no
thanks.
problem. Thanks. Okay, so let's say that, I don't know, let's say that eventually all this COVID crap is over and we get to, you know, sort of relax a little bit. It's spring break. This is you. Your arm's not attached to your shoulder, but it's spring break, so you're still excited. And you're over here by the lake. So there's the lake. And here's a fish living in the lake. He's also happy because he's on spring break too. Okay, so when water freezes, oh, I guess that wouldn't happen over spring break. So it's Christmas break, woohoo! And the water's gonna freeze. When water freezes, what's kind of peculiar about water that freezes, and this is pretty unique to water? Freezes on the top because ice is less dense. So you're both right. Ice is less dense than water. That's uncommon. The only other thing I know of that's like that is paraffin wax. So pretty much everything else, this is how like solid, liquid, and gas works. If something's a solid, all the particles are really close together. They're like barely vibrating, right? We think that molecules are always moving unless we reach absolute zero, negative 273.15 or whatever that was. We think at absolute zero, things stop moving, and we don't really know what happens after that. We think that atoms maybe just fall apart. We don't really know. So we're always trying to freeze crap down to absolute zero. And you're probably not super interested in it, but they've gotten within like thousandths of degrees. So they're like, hey, we've gotten down to negative 273.14999 or something like that, like thousands, 10,000s. They're that close. Great. So this is a solid. When they're farther apart, that's a liquid. When they're super far apart, that's a gas. That's how it normally works. But with water, it's different. With water, there's a bond angle on water. And I would say you never have to know this. It's like 101.5 degrees. Again, on AP Bio, you'll never have to know it. Apparently, if you go to UT, you'll be asked that on a test. I had a student come back one year that went to UT, and they're like, hey, Mr. Cotton, do you know the bond angle of water? And I'm like, I don't know. I'm like, it's greater than 90. I'm guessing, I know it's somewhere between like 100, 105. And they're like, we were asked that on a fill-in-the-blank question on a test. Is that important? I'm like, not to me. So it's like 101.5. Whenever you freeze water, it actually expands a little bit. So let's say I don't know what it is. I'll probably miss it on the test at UT. But maybe it's 101.6. So it goes like this. So now that means that ice is less dense. Let's say that I could fit 100 students in here, and they're all standing exactly like this with perfect angles. And then all of a sudden, I tell every single student, increase your angle by this much. Now can I fit 100 students in here? No. So if I cram it full with students and then I make everybody take up just a little bit more room, if the door's open, then now maybe a couple of students get pushed out the door. So now it only holds 98. What if the door stays shut and the walls stay here and everything else? What's going to happen to the room? We're going to knock down the walls, right? Think about this for a second. Pretend, you weren't expecting this, were you? Pretend that this was a glass bottle, like a glass Coke. Now, don't actually try this, because if you're strong enough, you're going to hurt yourself. But pretend that you have a glass bottle of Coke, and you can't just like hit it on the edge of the counter. You have to just brute forearm strength, break it. Just, here we go, slowly added pressure, try to break it. Can you? I bet not. It's super strong. Now, it's brittle. I could just go like that and probably break it. But if I'm just trying to crush it, it's really, really hard to break. Now, imagine I take a glass bottle. I fill it all the way to the top with plain old water, no carbonation or anything. I seal it airtight. I can't crush the bottle, even with my forearms. That was not a joke. Just kidding, it was a joke. It's okay to laugh. Sorry. So, I put it in the freezer. What happens when I come back a day later? Yeah, it broke the glass. So when the water does this, with greater strength than your forearms, which is pretty impressive if you think about it, those water molecules are going to expand their bond angles. So water expands when it's frozen. And so what that means is ice will float. So if I start forming ice crystals up here, they kind of float. So the top of the water freezes first. This is super important to life if you're a fish, because what that means is it's harder to freeze solid the lake. Let me show you why. Here we go. Here's the water. So now, let's say that a cold breeze blows across there. I get these little ice crystals, and they fall, and it starts freezing from the bottom. Now it's water on top. Cold air runs along, freezes the top, it falls to the bottom. Here, when the cold air runs across it, the water freezes and the ice stays on top. And now the ice actually insulates the water, it holds in the heat. So like down here in the ground, like 15 feet deep in the lake in Texas, it might be below freezing up here. Is it below freezing like 15 feet deep in the soil in Texas? No. So down here, let's say it's 40. So 40 Fahrenheit. Hey, are you in here now? Cool. Come on in. Back to class. Cool. Anywhere that you like. And have I had you in class at all yet? Yeah. Okay, cool. Sorry, I'm still kind of learning names and everything. So now what happens is this is 40, and that insulates. How does ice insulate? Like, how does ice keep heat in? It seems like that'd be cold, wouldn't it? Isn't that what an igloo is, though? You're out in the Arctic freezing, so what do? You get blocks of ice and build a little house. Why? To warm you up. So it might seem like it wouldn't work, but it does. So ice can act as an insulator. So all that heat hits the ice, comes back down, now the water is less likely to freeze solid. So that fish is thankful that ice is less dense than water. Yay! All right, one last water thing, and then we get to move on to carbon, which you guys will find the carbon stuff more interesting. The last water thing is pH. So what is it that pH measures again? Yeah, it tells me how acidic or how basic something is, or if it's neutral. And is water neutral? Yeah. What was the pH of pure, maybe not my tap water, but like pure water, what's its pH supposed to be? Yeah, it should be 7. Who thought that up? Like, why 7? Why not 0 or 10 or... Like why is it 7? It's not just because scientists decided it that way. Like, it actually is 7. Like, according to nature, it has to be 7. We don't have a choice. We have to call water 7. pH. Why do they write it funny? A little p and a capital H. Who thought that up? I mean, I guess I get why you wouldn't put a capital P and a capital H in a chemistry class, because you might think that that's like a phosphorus and a hydrogen. But why little p, big H? That seems dumb. That's on purpose too. pH works like this. Here's 7, neutral. If I'm acidic, am I higher than 7? Am I lower than 7? Which is it? Lower. So lower is an acid. Higher is a base. So here's pH. There's 7, that's neutral. Higher is a base. Lower is an acid. Why is that? This is also because of nature. So here's what it stands for. It stands for the power of hydrogen. That's why that H is capital. That represents hydrogen, technically hydrogen ions. So here's what pH is. How many hydrogen ions do I have? Well, if I have 1 times 10 to the negative 7th, what power am I raised to? Negative 7. They call that a pH of 7. What if I don't have this many hydrogen ions? What if I have 1 times 10 to the negative 2? What would my pH be? 2, because that's the power of hydrogen. My exponent, my power of hydrogen. Now we do have to ignore that negative, but that's the power of hydrogen. Okay, hang with me a second. So what would a pH of 14 be? What would my number be here? 1 times 10 to the negative 14. It's the exponent, the power, negative 14. You're like, all right, so why does this determine how acidic I am? Well, think back to chemistry. Is that an acid? HCl. Yes. It's hydrochloric acid. H2SO4. Is that an acid? That's sulfuric acid. H3PO4. Is that an acid? Now pretend that you had never seen H3PO4 before. Based on your chemistry class, how do you know that that's probably an acid? It does have an oxygen at the end, but this guy doesn't. Let me give you, see if this kind of reminds you. NaOH is a base. KOH is a base. CaOH2, calcium hydroxide, is a base. In 10th grade chemistry, you probably learned, yeah. Well, it depends, like, within that sulfate, that's covalent, but like, that side is positive, that's negative, so actually all of these are ionic. Now within there, that P and that O is covalent, but then the PO4 and the H is ionic, so it's not that. It's actually even simpler than that. Yeah?
Is it just that there's an uneven amount of hydrogen and oxygen?
Not a bad guess. It's not uneven. You're close, though. It does have to do with hydrogen and oxygen. Acids pretty much always start with an H. Bases pretty much always end with an OH. So, okay. The reason for that is how many H's you have determines how acidic you are. The more H's you have, the more acidic you are. So once again, I know that you're like, this is starting to get complicated, but that's why I video class. Which of these has more hydrogens? 1 times 10 to the negative 7th, 1 times 10 to the negative 2nd. Which one's actually a larger number? On like a number line, which is a bigger number? The bottom one, right? 1 times 10 to the negative 2nd is like 0, oops, let me pick a different color, is like 0.01, whereas 1 times 10 to the negative 2nd is like 0.00000001. So who has more hydrogen ions? This guy. The more hydrogen ions you have, the more acidic you are. So that's why pH 2 is more acidic than pH 7. All right. Why is water neutral? Like, did we just pick that as a base? Like, oh, we got to have something that we call neutral. Kind of like they kind of do in chemistry, that standard temperature and pressure. You know, it's 1 atm at 22 degrees Celsius or whatever. Why is water neutral? It's not that we just want to call something neutral. It's because water is neutral. Uh-huh. You're exactly right. Watch this. I could write water like this, H2O, but I could also write it like this. What do all acids start with? As far as you know, we're going to break this rule this year, but as far as you know, an H. What do all bases end with? OH. So what is water? Neutral. It's half acid and half base. That's why water is neutral. So you all are writing a lot of stuff, so I'll give you a second, and then I'm going to go over it again. Home crew, you guys still hanging in there okay? All right, cool. Curious George, you doing all right also? Sorry, I'll quit calling you out because you got the Curious George icon. I had to. Sorry. Oh, I got some thumbs up and stuff. Cool. Thank you, guys. Okay, so here was the overarching idea. You learned in 10th grade chemistry. Does that sound familiar now that your chemistry teacher might have said if you start with an H, you're probably an acid? If you end with an OH, you're probably a base? Or is that new information? You're like, I don't know, it's been a while, Cotton. So some of y'all might be like, my chemistry teacher might have said that, but I'm not confident, I'm not sure. So what we're going to learn is we're going to say anything that gives up H pluses is an acid, anything that takes them in is a base. Don't worry about that at the moment. That'll come up all year long. You'll get it. So here's what I want you to get. If I've got If I make hydrogen ions available, if I make H's available, I'm acidic. So anything that gives up H pluses is acidic. And it will have a lower pH. The more hydrogen ions I have, the lower my pH is. If I'm able to soak up hydrogen ions, they call me a base. The reason that water is neutral is because it has half of its properties are acid, half of its properties are base, so it's obviously like right in the middle. Just like debt. If I have plus $10, but then I've got negative $10 on my credit card, then I'm neutral, right? I'm at $0 total. All right. Now is where we start to slowly shift to bio class. Come on, cursor. There we go. Okay, this first picture, if you're live or at home, you will not be able to read this very well at all. So here's why we start with chemistry, and here's where we transition from chemistry to biology. This is a poster of the major metabolic pathways in a cell. So how many cells do we think the average human is? Obviously, if you're 7 feet tall versus 5 feet tall, the 7-footer has more cells than the 5-footer, depending on, body type. How many cells do we think the average human has? Like, is it 1 million, 10 million, 100 million, 1 billion, 10 billion? Like, give me some sort of number like that, like factors of 10. And I've actually got an answer. I'm not just going to say, yep, you're right, it's a lot. One of the most common anatomy and physiology books, we actually teach out of one of the versions. There's sort of like a big and a small version. One of the most common anatomy and physiology textbooks estimates that 1 cubic millimeter, not centimeter, but 1 cubic millimeter of human tissue has 1 billion cells. The average adult human, we think, might have close to 100 trillion cells. Okay, it's hard to grasp a number as big as 100 trillion. So I do this exact same exercise with my 9th graders. So for some of you guys, this might be familiar. If not, then it's a little bit shocking. So here's what we want to do. You will never have to know this on a test, but this is just for you to grasp how big of a deal this is. I'm getting ready to erase this. Did anybody need it, like a picture or anything? If you do, I don't see any cameras going up. All right, cool. You guys at home good? I'm recording, so. Cool, got some thumbs up. Thank you. All right, so real quick, this is just to appreciate how big of a deal this is. Anytime we're talking about stuff in biology, I get kind of like, even though it's my 23rd year teaching, I'm still shocked that all this crap works, right? With 2 weeks notice, we can't put together a master schedule that gets everybody in a class. But my body in one cell runs all these chemical reactions. We'll zoom in on some of these in a second. And I'm made of, say, 100 trillion cells, and they all have to work pretty much perfectly or I die. So how big of a number is like 1 trillion or 100 trillion? Like seconds. If I had 1 trillion seconds, how long is that? Like how many hours or days or weeks? Convert it to some obvious, oh, it's 100 trillion seconds, Mr. Cunn. I'm like, yeah. But how long is, we'll go with 1 trillion. How long is 1 trillion seconds? How long do you think? Maybe a few days? Okay, so maybe a lifetime is billions of seconds. So maybe more like 80, 90 years for billions of seconds. 150 years maybe? Well, let's see. Remember dimensional analysis? Let's do a little bit of that real quick. 100 trillion seconds. So that's 1,000 million billion, trillion. So this is just so you know I'm not making this crap up. And so you know that dimensional analysis is useful. By the way, second date when you're running out of stuff to talk about. This right here. So the first one was water chemistry. Now it's this. But it's only going to work if you have your pen. So don't look like an idiot. Have a pen. Otherwise, you can't talk about this with your date. I'm married. Like, isn't that bizarre? So 60 seconds in 1 minute. There's 60 minutes in 1 hour. There's 24 hours in 1 day. There's 365 days in 1 year. 1 trillion divided by 60, divided by 60, divided by 24, divided by 365. Do it if you want. I think it's 37,000 years. Again, you're welcome to calculate it real quick if you want. It's either 37,000 or it's 32,700-ish. Yeah. Sure. I don't have that pass thing pulled up, so I will give you a paper pass. There you go. You're welcome. Okay, so now, if I was going like this, or if I just like on my phone said go and it was counting seconds all day, every day, 24 hours a day, I'm snapping my fingers. I'm like 1, 2, 3, 4, 5, 6. It would take me over 30,000 years before I finally hit a trillion. But am I a trillion cells or am I 100 trillion cells? I'm 100 trillion cells. Did you get it?
It's 31,700.
Okay, 31,700. I thought it was 37 or 32.7, so 31,700. So I'm going to round down and call that 30,000 years. But again, I'm not a trillion cells, I'm 100 trillion cells. So I'd have to count for 3 million years. That's how many cells are in my body if I'm average sized human. What's happening in each cell? All of that crap. And if it messes up, I die. Yet I'm alive. Have been all year long. It's kind of mind-boggling, isn't it? Let's zoom in on some of this crap. And then I'll switch screens so you guys at home can kind of see it a little bit. It's super high res, so you can like zoom in on this. All of that is being managed. This part right here is photosynthesis, so you're not doing that little chunk right there. Everything else happens in humans that's on this screen. It also happens in plants, but we're humans, so we'll go with that. All of those. Super bizarre. These are all the major chemical reactions that are happening in a cell. Just the major ones that they all share in common. Then nervous system cells do different stuff from lung cells, from liver cells. So bizarre. We'll learn later on, that's the reaction right there that causes a headache. Aspirin blocks this from turning into this and this. And this causes the pounding and that causes the pain. So when you take aspirin, that chemical reaction doesn't happen anymore, and so now you feel better. Super weird. So all that is happening in you. So why would we start with chemistry? Because that's all we are. We're just a bunch of sacks of chemicals. How many? 100 billion of them. 100 trillion, sorry. So it's kind of mind-boggling. So that's why, yeah, you can just throw it away. So that's why all the time in here, as I'm teaching something, I'm like, I can't believe this crap actually works. This sounds like science fiction, you know, because it's amazing. Okay, so now let's look at something kind of interesting here. You'll see some chemicals that have like weird shapes up here. Like, let me find some of the carbs up here in the corner. So some of these carbohydrates, if I zoom in on them, they look like hexagons and pentagons and stuff like that. So do they actually look like that, or is that just kind of how we draw them? Like do we have microscopes of some kind? Special ones, of course. that can like see bonds and stuff? Like when I draw a water molecule and I use lines for bonds, is that because there's actually lines there? Or we got to draw something? When I was in AP Bio, they predicted this is what it looked like, but they couldn't prove it. And then, holy freaking crap, now we take pictures of it. That's what they look like. They actually look like that. There's a bunch of little hexagons and pentagons and little bent shapes everywhere. Like, that's 3 angstroms. I don't know how big that is. I know angstroms are super small. We're taking pictures of covalent bonds. One, 2, 3, 4, 5, 6 hexagon. Hex pent? Nope, hex hex. Hexagon, hexagon. So they actually look like that. Isn't that just weird as heck? Okay, now, let's look at something just a little bit different. Oh, I got to show you this. So now we have some fun pictures. That's a fire ant. Do fire ants bite or sting? They sting. Now they bite you to hold on while they shove their stinger into you, but you can even see a drop of formic acid coming out of his stinger right there. So here's some dude getting stung by a fire ant. And when acid's in your body, it feels like it's on fire, so we call them fire ants. So he kind of bites on with his little mandibles and then like shoves his stinger in. He's got a stinger kind of like a bee. Like, all right, so that's an acid. This kind of relates to pH very, very loosely. So that's a fire ant. Here's some guy. I don't know if I had to guess, he's high right now. He's just out in the middle of a forest, kind of like this, you know, like... But he's not. This right here is what's called a devil's garden. You're working your way through a forest, there's trees everywhere, picture like rainforest type of density. Then all of a sudden you hit this spot, and there's no trees. There's one type of plant, this type of plant. I don't remember the name of it, the genus species, but they call this a devil's garden. This isn't a bunch of plants. This is a bunch of the exact same species of plant. Almost like if I was a corn farmer, I've just got like tons and tons and tons of just corn, one species. This is all one species. And so if you're a tribal community, you're like, that's the devil. So the devil's killing all the trees, and the devil's garden expands year after year after year. So if you come back 10 years later, that tree right there might be dead, and it's being replaced by the expanding devil's garden. So scientists were trying to explain, like, what is it that's actually going on in the devil's garden? And here's what they found out. If you look really closely at the leaves on these guys, they're little hairy leaves. Hairs are on there so that herbivores don't think they taste good, right? Like I can eat a spinach leaf, but if a spinach leaf was covered in like fuzz like a caterpillar, I couldn't gag it down. So generally, fuzzy, thorny leaves are less likely to get eaten. But down at the base, there's this little bitty nodule, and if you're at home, you probably can't see that nodule very well, so we'll zoom in on it. If I cut through that nodule, it actually has ants living in there. So those are ants and their larvae. Like, that's kind of weird. What the ants do is they live amongst the plants. So the plants are providing a home for them. So is that a +1 for the ants? Yeah, that's a benefit for them. The ants actually eat some of the leaves, but not so much to kill the plant. So it sounds like the plant might be neutral or kind of harmed a little bit, but they're not. Because, this is true, the ants will go and sting to death all the other trees in the area, creating a devil's garden. So the reason that tree is going to die is because ants that live in this plant are going to go and sting it to death. Isn't that crazy? Can you imagine like watching ants swarm on a freaking tree? And then they sting it until it dies? And it's a tree? Isn't that bizarre? So, that's just me trying to make pH interesting. You'll never have to know that, unless you go on a third date. Then you'll need to know it. See, y'all are kind of enjoying yourselves a little bit more now. I try. All right, so if you're following along in your notes, down near the bottom, like quarter or so, I know you can't see it super well, but at the bottom of that page, it says carbon and biomolecules, versatility of carbon. Let's see, 10:30. Yonda said that they had technical difficulties, was what the email said for TCTV. Let me double check. Oh crap, that's a whole lot of email. He's not on the page anymore. Yeah, due to technical difficulty. Okay, so let me gather my thoughts for just a second. We got till 11:04. Get that. Okay, cool. We'll get to end on something really interesting. So when I'm looking at carbon and biomolecules, remember with biochemistry we had CHONPS. How many bonds did carbon always form? 4. I can look at a periodic table if I want. Let me switch camera angles for you guys. I can look at a periodic table if I want, but carbon is in column 4, so it needs to gain and move over to column 5, 6, 7, and then 8, the noble gases. Hydrogen always forms 1. Oxygen always forms 2. Okay, well, in that little section of notes that says carbon and biomolecules, we're going to look at where it says shape and functional groups. So it's down near the very bottom of the page pretty much, where it's talking about shape and functional groups. So when you were in your chemistry class in the past, you didn't care about the shape of molecules very much. You mainly cared about, is it, let's see, calcium hydroxide. Do I have one of these and one of these? Or, oh no, it's 2, so I have that. You know what I mean? You're mostly concerned about, if I have 1 calcium, how many of these do I need? That type of thing. In bio, the shape of molecules and their chemical characteristics matter a lot. You can just trust me, or you can flip around if you want, but on the front page, the only statement in bold all caps is at the bottom. It says 3D shape and chemical character matters greatly with organic chemistry. If you flip to the next page, the only thing in bold, all caps, other than like a title, is about 2/3 of the way down. It says 3D shape and chemical character is everything. So that statement is in there twice. And it's the only statement that is bold and all caps. So 3D shape and chemical characteristics matter a lot. So they have these things called functional groups. And this is the last kind of memory thing. And then we get to apply it to something really interesting. There are certain chemicals that we just kind of see together. You do not have to memorize these functional groups right now. But they're just certain chemicals that we see together a lot. And when we do, we name those, like OH. We see that a lot. Let me prove it to you. I can go back to the metabolic pathways of life, zoom in, and you'll see a lot of O's and H's, OH's and HO's. So as I'm just going through there, OH, HO, OH, OH, CH3s. Depending on where I move on this chart, I just see different groups of chemicals together, and so I give them a name. So like OH we call a hydroxide. You might remember from your chemistry class. What was that called? PO4. Yeah, phosphate. It has a 3 negative charge. Phosphate, that's a functional group. So we have certain functional groups that we're going to end up seeing. Don't worry about memorizing them now, but by the end of the biomolecules unit, did that just go? Hang on. Okay. Do you guys have an echo for me, like my microphone, or is it okay? It's okay? All right, cool. First, just a second, this microphone turned on. So those are functional groups. So we will use functional groups throughout. But here's one of the important things that I wanted to show you. Let me switch camera for the home crew. And that is this. This will end up being the most interesting thing that you see today, like out of all of your classes. Promise. Not this picture, but what it's going to explain. Isomers. Down at the very bottom of your notes, the last 2 lines talk about isomers. What is an isomer? Like if I look at this compared to this, and they're like, that's an isomer. What do you think an isomer is? And I might have even put it in my notes, I don't know. But what do you think an isomer is? Yeah, it's the same number of atoms, but they're just arranged differently. So the chemical formula for this, by the way, would be like, I have 1, 2, 3, 4 carbons. So it would be, over here on my whiteboard, I'm writing C4. And then how many hydrogens does it look like I have? 10. So it'd be C4H10. What about this guy right here? What's his chemical formula? C4H10. Are they a different shape? Yes. In biology, does shape matter? Yes. So it turns out that's C4H10. That's C4H10. If I put that in my body, it has one effect. If I put that in my body, it has a totally different effect, because shape matters. All right. Even down to this. So an isomer is if you have the same chemical formula, but a different structure, a different arrangement. For example, in your 9th grade class, you guys learned that C6H12O6 was glucose. That's also maltose. And they taste different. That's why you can get a shake or a malt. A malt is made with maltose sugar. And its shape is different. So it reacts with your tongue differently. So it tastes different. Even this, down here at the bottom, oops, these guys are mirror images of each other. So at first, if something's a mirror image, at first it seems like you could just spin it and like make it work. So let me show you what I mean. Let me flip on, maybe that light will help them out a little bit. So let's say I've got this. That's purple. That's black. And I think I'm right in the sun thing. Would one of y'all mind twisting those blinds so that it'll shut, please? Somebody kind of back in the back there. The little twisty thing is on the left. Yeah, thank you very much. Thanks. Okay, so pretend that I'm a chemical. And this on the board is a receptor in my brain, or a receptor on my tongue. If my chemical matches this, then I sense it. So right now, I've got a chemical. This is purple. This is black. This is orange. So as is right now, maybe I've got something coming out the top like this. So I've got purple, black, orange, and red. This is the shape of this chemical. Right now, I can get it to fit to where black touches black. Let me make it a little bit farther apart. There we go. So in my brain has these little sensors, and it's trying to sense this chemical. So for it to, my brain again is the wall. For my brain to sense this, it has to like touch. Black has to line up with black, purple with purple, orange with orange. And right now it does. Black, orange, purple lines up with black, orange, purple. Cool. So that works. Now watch this. I'm going to switch. Purple and black. Doesn't it seem like I ought to be able to twist this and make it work? But I can't. No matter what I do, it doesn't work. So my body sees this as a totally different chemical. Like, all right. So the point I'm trying to make is isomers are when you have the same chemical formula, but a different shape. And shape matters. So if you have a different shape, your body views it differently. Okay. So if I have a mirror image, it seems like if this is my right hand and this is my left hand, they're mirror images. This is my right foot. This is my left foot. They're mirror images. Doesn't it seem like if I put out a left shoe, I ought to be able to just sort of like turn my right foot a certain way and should be able to get it to fit? But does it? No. A right-handed glove and a left-handed glove, it seems like, but they don't. Same thing here. They're mirror images. So why does this matter? It matters because of that. So, what is that? Took this picture this morning in my kitchen. That's crystal meth. Methamphetamine. I'm joking, of course. Y'all seen Breaking Bad? The science teacher that makes meth. It's a really good show. Pretty dark, but it's an awesome show. Like best Netflix series I've seen. They even had a spinoff off of it called Better Call Saul from like a secondary character from the show. If you liked Better Call Saul, this is what birthed it. It was even way better. Okay, so methamphetamine is a problem. I always have to re-Google it because I can't quite read it. It's like Multnomah County Sheriff's Office. So there are places where meth is a big problem, and this is one of them. So what they do is if you Googled faces of meth, you would come across this site. And on the Faces of Meth site, basically what they do is they take pictures of people. They get arrested, of course. And then if they're busted for meth and they take their picture later, they post it online and they tell you how much time has passed. Again, this is from the Sheriff's Department website. So it is real. It is legit. Now, I'm 44. Trying to think of who else you guys know. Trying to think of who's in their 30s. Hacelius next door, she's not yet 30. She's close to 30. She's like upper 20s. How old does this lady look to you? I'm 44. You might know somebody. Maybe you have a parent or something that's in their... Are any y'all's parents 44-ish? Wow, I could be your dad. So you can probably kind of picture, you might have a gap of people in their 30s. I wish I knew more teachers' ages. How old do you think she is? How many of y'all think that she looks like she's in her 30s? How about 40 to 45? 45 to 50? How about below 30? All right, so that's kind of scattered everywhere. It looks like 30s was kind of the most common. Now, obviously, she's only 2.5 years older, but how old does she look? The class average is saying this person looks 30s. How many of y'all think that she looks like she's in her 30s? 40s? Again, I'm 44. Uh-huh. How about 50s? 60s? A bunch of hands went up on 60. So there she looks 30s. There she looks 30 years older. And how much time has passed? 2.5 years. If you go to the Faces of Meth website, there's a bunch of them. Now, if you're on the camera, you might not be able to tell. Spoiler, they look worse. Some of them, occasionally, you'll find yourself, it's kind of comical, and you laugh, and then you're like, wait a second, that's a real person. That's not like an actor on TV or something. So it's, but at first, it almost looks comical, right? I mean, that doesn't even look real. I'll try to zoom in on a few of them for y'all at home. But again, if you really wanted to see higher resolution pictures, Faces of Meth. And it should come up on some sort of something county sheriff's site. Okay, now, what you'll notice in a lot of people is that they seem to have like some skin problems. Like This guy here, all of a sudden, he seems to have like scabs and stuff. The lady next to him, you know, skin looks pretty normal. Now it looks like she has like scabs and like skin infections and stuff like that. One of the things that meth causes, and I can't remember the technical name for it, but you feel like you have bugs under your skin. So you end up kind of tweaking or whatever, but there's like a medical name for it where it feels like you have creepy crawly skin, and so you kind of scratch a lot. And so because of that, you get a lot of scabs. More scabs means more likely to have infection, and so that's why like her face and eyes kind of swollen, because it's probably just like an infected scab or something like that. You're like, all right, I think we're talking about meth now. We've also got meth mouth. Turns out people that inject methamphetamine also get meth mouth. So it's not because you're smoking it and it's like the smoke that's causing meth mouth. You know what causes meth mouth? Not brushing your teeth. You're like, why don't people on meth brush their teeth? Because every minute that you're brushing your teeth is a minute you're not seeking meth. So, quick little life lesson. I've never done meth. And you know why I'll never try it? Because of that. Not out of vanity because of my teeth, but I kind of have this thought experiment in my head. All right, what would it take, and I told this to my 9th graders too, so what would it take for me to just not brush my teeth? I don't mean miss it once in the morning because I forgot and I ate an apple so they still felt kind of clean or something like that. But like, what would it take for me to day after day not brush my teeth? Sounds horrible, but like, if my wife died, I'd be crushed. Hopefully, I would have the energy to call into work. If not, I'd probably just text somebody, my wife died, I won't be there, figure it out. I probably wouldn't shower that day. I might not brush my teeth that day. I'd be so nauseated I probably wouldn't eat. But the next day when I woke up, I better brush my teeth. I'd be horribly depressed. I'd be crushed. But I bet I'd brush my teeth. You know? Like, at some point, I would. What would it take for me to not? So let's say that my wife or my son was kidnapped. That's probably what it would take. I'd get in my car. I'd run out of here like a crazy person. I wouldn't tell you where I was going, or I might, as I'm running out the door, yell. I wouldn't stop and like send an email, because the faster I get in the car, the faster I can find my son, the closer he'll be, the less likely he is to get away. So I wouldn't brush my teeth. I wouldn't sleep until I like collapse. The only time I'd pull off the road is to like sleep, because like I'm going to wreck, and I'm not worried about me, but then I can't find my son. If I was out of gas and the gas station was closed, I would steal gas, because I'm trying to find my son that's been kidnapped, and I would never stop and brush my teeth. So the reason that I won't take meth is whatever is in that crap, methylene dioxymethamphetamine, if you're taking ecstasy is also a type of methamphetamine, but whatever is in there is so strong that it makes people do this. And the only way for me to behave like that is for something to be so strong that it's like somebody in my family was kidnapped. So that is some heavy-duty crap. All the major, common, worst things that could happen in my life, I would still, within 24 hours, probably brush my teeth. You know what I mean? So that meth addiction, that's got to be strong stuff. Okay, with that in mind, now, let's look at this. Let's say I've got an allergy problem. Vapor inhaler, Vicks, nasal decongestant. Active ingredient, levmethamphetamine. In English, we say levomethamphetamine. It's methamphetamine. You're like, wait a second. People don't leave their families or lose their jobs over Vicks vapor inhalers. That's because this is left-handed methamphetamine. It's levomethamphetamine. The addictive meth is right-handed methamphetamine. They're mirror images of each other. They're isomers. One of them hits my brain one way, and now I'm addicted to meth and I'm going crazy. The other one has no effect on my brain, and it hits my nasal passageways and acts as a decongestant. So it's almost like I've got a glove over here, and if I stick my right hand in it, then now I'm addicted to meth. But if I do this, it fixes my allergies, because shape matters. So this is what they call, back over here, the slang version, scientists on the street, right? You don't want to get made fun of by the other scientists. So on the street, they just call these left-handed and right-handed chemicals. Oh, is that the left-handed methamphetamine or the right-handed methamphetamine? Why does it matter? Oh, it matters. It matters a lot. Snort that one or snort that one. Difference is big. So the shape of a chemical matters. Let me give you another example. This is a drug. Outside of a biology class, the only place you might have heard of this would be in like a world history class, but that's still highly unlikely. This is called thalidomide. Has anybody ever heard of thalidomide? If you are curious, thalidomide. I realize at home you can't see that, but it is how it sounds. thalidomide. You don't have to know thalidomide. I'm just giving you an example. One of these is the left-handed version, one is the right-handed version. This is a boy whose mom took thalidomide. He has no arms. He has a shoulder and a hand, but he has no forearm. He has no upper arm. It's because his mom took thalidomide. 2 lessons from this. This kid is likely German, because in Germany, thalidomide was legal. If you're a mom and you're pregnant, especially the first few months you're pregnant, the first 3 months or so that you're pregnant, the first trimester, a lot of moms get nauseated, and they call it morning sickness. Morning sickness. They wake up, they're pregnant, they barf. Well, if you wake up and barf, drink some water, and a couple hours later you're able to eat a meal, it sucks, and this is going to sound callous, but like, you'll be okay, your baby will be okay. But what if you wake up and barf, and every time that you put anything in your mouth, you barf? Isn't your baby going to be like missing out on calories, and aren't you, and nutrients and everything else? So at some point it becomes an actual problem instead of just like, hey, that's gross, it's inconvenient. At some point, like, it's a danger to you and your baby. So anti-nausea medications. When you're pregnant, do you typically want to take medications? No, but at some point you're like, what's worse for the baby, a medication or being malnourished? So they had this drug called thalidomide. They tested it on mice. We'll end with this. They tested it on mice. So they thought it would work in humans. Why do we think that things that work on mice would work in humans? Because we're about 85 to 90% genetically identical to mice. So in general, whatever works for them works for us 85, 90% of the time. So they tried thalidomide on the mice. They gave them one version. I can't remember which one was okay and which one wasn't. One of them, when they gave it to the mice, basically it fixed morning sickness. In mice, they can get morning sickness too. The others, when they gave it to them, the moms birthed kids with limb deformities. So again, let's say it was the left-handed one was good, the right-handed one was bad in mice. And they're like, all right, be careful. Make sure you only give the left-handed version one to humans. And in Germany, they're like, let's go ahead and sell this. In the US, the FDA was like, no, we haven't tested it enough. So then they gave it to mothers in Germany. Turns out humans have an enzyme, and it grabs whichever version of thalidomide you have, and it just randomly flips them back and forth. So we gave all these German mamas the left-handed version. But once it got in their bloodstream, it's being flipped back and forth. So half of the molecules got flipped over. And so about 100,000 German kids were born with limb deformities. All because right-handed versus left-handed thalidomide makes a huge difference. One is good at curing morning sickness, the other causes this. How many Americans suffered from this? Very few. Only those with like German family that mailed it to them. That was years ago. Now imagine the people that this happened to are probably currently in about their 80s. So about 80 years ago or so. Imagine now in the modern internet age what would have happened. You're in the US, you hear that there's some drug for morning sickness. You have morning sickness. It's available in Germany, but it's not legal here. How many people would just order it over the internet anyway? How many people order Xenadrine or some other weight loss drug from Canada because it's legal there and it's illegal here? So we were lucky. If thalidomide, if this whole thing had come up now in like the 2000s, there'd be tons of Americans and tons of people all over the world that would have limb deformities because they would have just skipped it and said, FDA, what? Are they here for my safety? I don't trust them. They're the government. And you'd have gone and got your stuff from Germany. So 2 lessons. Number 1, shape matters in biochemistry. And number 2, careful. If the FDA says no, careful. Don't just get on the internet and buy it from some country where it's legal, whatever it is. All right, we'll stop there for today. Let me switch back cameras. All right, home crew, you guys doing okay? Okay, pretty good. Just to be clear, for attendance and stuff, since you guys are at this, that's your attendance. If you ever want to come to any of the like after school times to ask a question or something, you can, or that 6th period option, you can. But basically, you're just sort of here live with everybody else. So if you have any questions, let me know, or if you're having any ideas about how to make this better for you guys, just email me or let me know somehow. And otherwise, hope you guys have a good rest of your day. So if you're here with 3rd period, then see you later. If you just popped in and you're actually in 5th period, we've got, I have lunch now, don't I? Yeah, I have a lunch now. So we get started at 5th period. We'll start at 11:45. So.
I have a quick question.
Yes, Ashley.
So because Monday was an odd day, are we leading with odd days right now?
Yes.
Like, we started instruction on Monday.
Yeah, what I'm doing as far as videos go is I wanted to get a video uploaded to YouTube right away, so I uploaded yesterday. But this day is actually a little bit farther along. So basically yesterday stopped at like say step 6 or 7 on water. So now odd's a little bit ahead of time. So what I'm going to do is I'm going to take this odd video and throw it in there, and then from now on we're going to be following odd. So odd is ahead.
Okay.
Yes. So what you're going to find if you go to the YouTube is you'll be like, he put in a video yesterday and today, and then when you start watching the videos, they'll overlap quite a bit. And then from now on, I'd said I would video 2nd period, but I'm actually going to be videoing 3rd period.
Okay.
So, and it looks like they upload pretty fast. At home, it takes like an hour and a half to upload it to YouTube. I uploaded it the other day, and I thought it was just like skipping screens. It took like 7 seconds. So their upload speeds are incredible. So I should be able to like get this video whenever I get a chance and get a break today. I should have it uploaded. So like if you missed it, like it should be in there like this afternoon.
Okay.
All right. Thanks, Ashley. Any other questions that you guys have?
I have a question. Do we have any homework, like reading another chapter in this class?
Yes. So if you go into the Google Drive, there'll be a syllabus page. It's going to look like this.
Please release our Falcons in the field house, portables, and downstairs North Hall, along with those heading to a K-Cal class.
So if you're just in the Google Drive, I think it's on its own. It's not even in a folder, but it'll say like what we do next. So what we're supposed to do next is read chapter 2.4.
Okay, thank you.
You're welcome. Yeah, no, it's a little bit puzzling. I think that we'll have a pretty solid plan soon, though. Anybody else? I see that Curious George is unmuted. Is that on purpose because you have a question? Oh, sorry. Wasn't trying to call you out, George. All right. Well, if you were here for 3rd period, you're free to go. And thanks for coming. I know it's a little bit tricky buzzing in from home. So, bye. Or I guess I'm over here. Oh, you're welcome. I'm trying hard.
Please release
Yes, Angela.
So, I finished that textbook reading. I did the 3 pages.
Uh-huh.
How do I turn it in?
That's a good question. I want to get Canvas up and rolling because that'll be the easiest way for you guys to turn it in. So for right now, you can hang on to it. And what I'm going to do is like at the very end of the unit, I'll kind of make it do then. So if you want, you can just keep it all until the very, very end of the unit and then turn it in. Or if you want to turn it in like a little bit at a time, it'll probably be easier for me if you just turn it all in at the end all at once. So for now, I would just hang tight.
Okay.
So thank you very much. But I'm going to try to get Canvas up and running this weekend, and that'll be probably the easiest way for you guys to turn stuff in.
Okay, thank you.
Oh, you're welcome. Anybody else? If not, you guys are free to go.
Please release our Falcons in upstairs North Hall, upstairs Center Hall, and Athletics Hall.
It's almost us. All right, cool. We'll start back about 11:45, so I'll see you guys then.